exponential growth in discrete time, and that's sometimes called geometric growth. And we're seeing two formulas. The one on the left is a general formula, and here if you just know the initial population size and the parameter lambda, then you can calculate the future population size for any time that you're interested in. On the right hand side, the formula, you can only calculate the population size 1 year into the future. So that's the difference between the two formulas, whether they're useful for only 1 year or for any time. These equations are called discrete time because you're using the current population size to predict the future population size, like you see on the right hand side, and the increment of time is per year or per unit time, so there's discrete time intervals. This equation is appropriate for populations that have regular pulse reproduction. So the pheasants are a good example of this because they reproduce once per year in the summer. And so the reproduction is regular because it happens every year, and it's pulse because it happens just during a short time of the year. So pheasant populations have regular pulse reproduction because they reproduce every year during the summer. So can you think of any other species that reproduce like this and would be better modeled with a discrete time equation? I'll pause the video and let you guys talk about that as a class. In contrast to discrete time, we have continuous time, and we can also have exponential growth as a continuous time equation. So this is appropriate for species that reproduce continually throughout the year. So let's ask the question again. Can you think of species now that would be better modeled with a continuous time formulation? These are species that reproduce continually throughout the year. Let's pause the video and discuss that. When you're working in continuous time, we use an ordinary differential equation to describe how the population is changing, how the population size is changing with respect to time. We have a small notational change, which is in discrete time. You might remember we had the population size at time t be denoted with n subscript t. Now that we're working in continuous time, we're denoting the population size as n is a function of t. So those brackets say that it's a function of, the round brackets. This is just so we can keep track of whether we're working with a continuous time or a discrete time model formulation. So that derivative that you see on the left, that's an ordinary differential equation. It's an ordinary differential equation because you have a derivative with respect to the independent variable. The independent variable is time. So it's different than some equations that you might see in a normal calculus class, because the derivatives that you see in a first year calculus class and not an ordinary differential equations class are not with respect to the independent variable. So you don't need to know ordinary differential equations to take this class. You can understand what an ordinary differential equation is just by using some knowledge that you have from a normal calculus, first year calculus class. And what's important is to realize that a derivative is the slope of a graph. And in particular, if we have a graph of the population size versus time, that derivative on the left there would be the slope of that graph at a particular point, tangent to the graph of the population size versus time. You can also think of the derivative as being a rate of change, but rather than being a rate of change over a discrete time interval, it's instantaneous at a point. So it's an instantaneous rate of change. That's what that derivative is on the left. And the other thing that comes up in calculus is that if the slope, so if that derivative is positive, then it means that the population is increasing, and if it's negative, it means that the population size is decreasing. And again, That's something that you learn in calculus about the interpretation of the derivative. It tells you whether the quantity that you're taking the derivative with is increasing or decreasing. That's what the derivative is. So you don't need to know ordinary differential equations. Just try and interpret this quantity in terms of whether the population size is increasing or decreasing based on the sign. So the general equation for continuous time formulation is that the rate of change is equal to things that are making an increase minus things that are making a decrease. So the rate of increase minus the rate of decrease. And in the simplest case, exponential growth case, then our change in population size, so this is the rate of change, is equal to things that are making the population size increase, which would be the birth rate, minus things that are making the population size decrease, which are mortality, or in other words, deaths. So we're just thinking about things that make a positive contribution and things that make a negative contribution. The change in population size with respect to time is notationally written like this derivative, and the birth rate is going to be defined as a per capita birth rate times the number of individuals in the population, and a per capita death rate times the number of individuals in the population. And these are just the definitions of B and D. So they're per capita rates of birth and death, number of births per individual per unit time, probability of dying per unit time, or per capita death rate per unit time. So we can just take that equation and factor the B and D into brackets, and then we get the form of exponential growth that you're used to seeing, where R is now defined as the intrinsic rate of natural increase, and it's the difference between births and deaths. So let's just recap what we know about discrete time and continuous time. If you look at these equations, the right-hand sides look very similar. You have lambda times the population size on the left, and R times the population size on the right. So in both cases, you have a constant multiplied by the population size. So that side's very similar. The left-hand side of these equations is not very similar. In one case, we're predicting the population size 1 year into the future, and over here, we know if the population is either increasing or decreasing based on the sign. So these equations, while they might look quite similar, are not really that similar. On the left, we have that the population is increasing if the population size next year is bigger than the population size this year. And on the right, we have that the population is increasing if the derivative of the population size with respect to time is positive. So given that, try and think about for what values of lambda does the population size increase, and for what values of R does the population size increase. I'll pause the video while you think about that. So far what we have is just an equation that tells you if the population is increasing or decreasing, but we might like to know what the population size actually is. So now Mr. Fofana is going to solve the ordinary differential equation for exponential growth, and you'll see where the exponential part comes from the name for exponential growth. And we'll pause the video and he'll go ahead and do that now. Just to check your understanding now, so we have this expression that tells you what the population size is at any point in time, if you just know the initial population size and if you know R. So here we start with some really small initial population size, And in this example, I've chosen r to be equal to 0.5. So we know that the relationship between the population size and this ordinary differential equation is that we can think of the ordinary differential equation as being the slope of a tangent line to a graph of the population size versus time. And so just drawing that in, I'm going to ask you guys if you can figure out what the slope of this tangent line is, because we know that r is equal to 0.5. And I also want you to tell me if the slope of the tangent line is positive or negative. So pause the video and I'll have you guys write that down on your piece of paper. I thought it'd be nice to have everything that you need to know about, or all the facts about discrete time and continuous time exponential growth formulations all in one place. So we have two equations for both continuous time and discrete time. The top equations are really just saying that the per capita birth and death rates are constant, and these equations are telling you for discrete time the population size next year, and for continuous time whether the population is increasing or decreasing. The bottom formulas are telling you what the population size actually is at a particular point in time. And if you notice, if you let lambda equal e to the r, these equations are actually exactly the same. To decide whether you want to use a discrete or a continuous time formulation, you want to think about how the population distributes its reproduction through time. So for a population like pheasants that reproduce, have regular pulse reproduction, so they reproduce every summer, you want to use discrete time. For a population that reproduces continuously throughout the year, like bacteria, it's better to use continuous time. So sorry, I don't know if I said discrete time for pheasants, but on the left here, for pulse regular reproduction, you want to use discrete time. For discrete time, the population size is increasing if the population size next year is bigger than the population size this year. For continuous time, the derivative of the population size with respect to time needs to be positive. For discrete time, lambda is always non-negative, because it's 1 plus b minus d, where d is the fraction of the population that die in each time step. So d is less than, it's between 0 and 1. B is the amount of reproduction, so this is some positive number, or 0. So lambda, the smallest value it can take is 0. That would be if everyone in the population dies and if there's no reproduction at all. So lambda is non-negative. But it's different for r. R can be positive or negative, because r is just the birth rate minus the death rate. So the death rate is the instantaneous death rate. So that's the number of individuals that die per unit time. And so depending on what the unit time is, this can be either bigger than 1 or less than 1. So r can be either positive or negative, and the population grows if r is positive. In the case of lambda, you have to think about lambda in the context of this equation. If lambda is bigger than 1, then the population increases. And we have different names for lambda and r. So lambda is called the finite rate of population growth, and r is called the intrinsic rate of natural increase. So to summarize what the main points were, exponential growth assumes that all individuals in the population have the same chance of dying and produce the same number of offspring. So the per capita birth and death rates are constant, and they don't change over time. And especially notably, they don't change with the size of the population. And the other main point of this lecture is that we can use mathematical formulas to predict the size of the population in the future. And so early on in the class, we talked about what population biology is about. And one of the things that came up was that we might like to predict population size and understand how the population is changing. And exponential growth is the easiest, simplest way of doing that. So hopefully everyone was okay with the amount of mathematical manipulation that went on today. I just wanted to let you know how important it is to do these things in an ecology class. So a survey of 937 early career scientists who studied biology as an undergraduate found that 75% were not satisfied with their understanding of mathematical models. 75% felt the level of mathematics was too low in their ecology classes, and 90% wanted more mathematics classes as ecologists. 95% wanted more statistics classes. So maybe you don't realize it now, but a really high percentage of people who go on in biology really wish that there was more math presented in their classes. So hopefully maybe you don't appreciate that now, but I'm just trying to look out for what you probably want, what your future self would probably be most happy with. Next class, we'll start talking about density-dependent growth and logistic growth, and you have some reading due that's relevant for that lecture.